Okay, here's another video here, and this is on the experiment problem that's on the 2016 AP test. So here we go. A new kind of toy ball is advertised to bounce perfectly elastically off hard surfaces. A student suspects, however, that no collision can be perfectly elastic. This is true. The student hypothesizes that the collisions are very close to being perfectly elastic for low-speed collisions, but they deviate more and more from being perfectly elastic as the collision speed increases. And we want to design an experiment to test the student's hypothesis about collisions of the ball with a hard surface. The student has equipment that would be normally found in a school physics lab. Okay, so first off, let's kind of review. In order to do this, you have to understand what a perfect elastic collision is. Essentially, remember for all collisions, momentum is conserved. So momentum is conserved. But this we're looking for essentially that the initial kinetic energy is equal to the final kinetic energy. And I should have just wrote K instead of KE, but there we go. So I'm going to kind of draw a diagram here. I think this will probably get this across the best. So I'm sure we've all dropped a ball before. Maybe you've done an experiment kind of like this before. So here's going to be my surface. So this can be any sort of like tile surface. And I'll just make this my ball, I guess. So my ball is going to, when it falls, dear, having a hard time doing that on here. Alright, it's going to fall, and then it's going to hit the ground. And then it's going to bounce back up, but it's not going to go up all the way. Oh boy. Alright, better. Okay. So let's say it does something like this. So, right now, right at the very top that we're dropping this ball from, it only has gravitational potential energy. Okay. Here, it has only kinetic energy. Okay, but that kinetic energy, right before it hits the ground, is going to be equal to that initial gravitational potential energy. And then here, when it kind of stops, this is kind of our final gravitational potential energy. And that's going to equal essentially the kinetic energy when it leaves the ground. So if we're looking to see if it's elastic, so does that initial kinetic energy equal the kinetic final energy? Well, we could easily do this by just seeing if this drop height, see, does this height equal this height? So does the drop height and of course we know the answer. It's going to be false, but and I'm going to call it the bounce height. Alright, because if we know the height, the mass of the ball is not going to change. This is going to tell us, comparing the initial gravitational potential energy to the final, which, like I said, is going to be related to the kinetic energy. Okay. Alright. So, what quantities would be measured? Well, this is what I said. We need to measure the drop height and the bounce height. Okay, that's what we need. So for A, part 1 or whatever, we need the distance we drop it from, and we need the bounce height. Alright, and having the ball's mass would help, just because we would actually be able to get things in terms of energies, but it's really not going to change the experiment much. Okay, what equipment will we need, and how would it be used? Well, we're definitely going to need the ball, meter stick, I would say we would need probably some tape. The tape could help us make sure that the meter stick is perpendicular to the floor, and if we had a slow motion video, right, that's pretty standard equipment. Slow motion camera. So, technically you could do this with photo gates too, to measure the velocity, but if you're talking about the easiest, the quickest way, all you got to do is drop it, measure the height you drop it from, and measure the height that it bounces up to. Okay, so how would it be used? Well, I don't even think I need to identify the ball here. So this is going to measure the height. I should have written this a different way. Measure the height. This is going to keep the meter stick parallel. And then this is going to help identify the bounce height. All right. Now we're going to look for our procedure. And so it's really important that you don't just skip steps here. We need to be very careful about what we say. We want to be able to get the maximum points here. So usually the cases with these experiment problems is that they're looking for the most direct way to solve. So kind of like the simplest, not kind of like the most low tech that you can possibly be, unless it otherwise states it. Because this is a pretty simple lab, and I actually did this with my general physics class just about a week ago. So the first thing you want to do is want to measure the height that you drop that we drop the ball from. And when you're doing this, we need to make sure we measure it in a consistent way. So we need to measure this height in a consistent manner. So what I mean by that is, if this is your meter stick, and you have your notches, if you're going to position the ball like this, okay, you're going to, let's see, we'll make it like that. So I would say it's going to be hard to judge the middle of the ball, and it might be hard to judge the top of the ball sometimes. So just kind of making sure that whatever method that you choose, that you're consistent. So if that's the bottom of the ball, that's going to be how you're going to measure. So you could write something like that. So we want to kind of point that out. All right. So, you could include here however you wanted to measure it. Okay. Then we want to tape the meter stick to a wall. And so the reason why we want this is to make it perpendicular. And this will reduce random error, or systematic error, I guess you can say. All right. Okay. Okay. So after we have those two, we're going to want to set up our camera on a stand. So the reason why I say that is because, if someone's holding it, you could not be videotaping it perpendicular, so like straight on to the meter stick. So you would want to set up the camera on a stand so that it faces the meter stick directly, I guess. And I'm going to try writing it on the other side of my pen. There we go, that's a little bit easier. I do like my stylus, but it's still harder than using a pen. Okay. Alright, so I'll say kind of like our fourth step is that we want to drop the ball from, 10 is a good number. Let's say drop the ball from 10 different heights. So, you could make up something. We could say ranging from 50 centimeters to 150 centimeters. So 10 centimeters in between. It would not matter. It would be better if you skip the same amount, but The reason why we want such a range here is that 50 centimeters would be relatively, pretty low velocity, so low impact speed. And this is, going to be higher. And that it kind of said that in our in the prompt. It said that it was pretty elastic at low velocities, but not at higher ones. So this would kind of help us test that. And then, basically, we're going to drop it. And, you could say something like repeat, 3 to 5 times, whatever, for each height. Okay, so a pretty simple procedure here, but I try to include all the details. Oh, I did actually miss a very important step, and that would be to measure the bounce height. Duh. From our video. Okay, I think that's good there. And the next part of the question is we want to describe how we would represent it in a graph or a table. Explain how that representation would be used to determine whether or not the data is consistent with the student's hypothesis. So I think the easiest way here is to go the route of doing a graph. So the reasoning here, comparing the drop and the bounce height, remember at the very beginning it said that it was very close to being elastic very close at low speeds, but it became less elastic as the speed increased. So really what we want to do is, let's make a nicer graph than that. We basically want to make a graph that was the drop height, so we'll do the bounce height here, and drop height. All right. So you don't actually make the graph, but you want to explain what would happen. Okay. So I'm going to kind of draw mine out just to help explain to you guys, but this should be pretty verbal. So kind of think of it of how I'm writing it out or talking. All right, this is getting in my way actually. Okay, so this is all right. So we started at 50 centimeters, 0.6, 0.7. Okay, and honestly, I probably don't need to be doing this, but 7.8. One more, 1.3. Okay, so let's say the way our data is at low speeds, it was very elastic. So you want to explain what that means. If it is nearly elastic, remember that means that the bounce height is going to, be very close to the drop height. Okay? And if you're looking at their hypothesis, then eventually the bounce height is going to be getting less, so much less than the drop height for high speeds. Okay, so you would want to describe how that would kind of play out. So let's say it went kind of like this, and let's see. Oops, let's see this. Okay, so we can kind of see here that these are pretty close to being elastic, but they're kind of getting less and less elastic as it's going on. So this is the type of relationship that the student is looking for. So if you're a math heavy person, then you could explain that towards the bottom that the slope, so like if your trend line here would be close to 1, be about 1. But as you get further, not only does it become less linear, but the slope, is going to be less than 1. Meaning, that the bounce height is going to be much smaller than the drop height. But if you're more strong verbally, then just simply kind of explain it in terms of words. All right, I feel like I'm rambling on. So, on to part C. Okay. A student carries out the experiment and analysis describes in part A and B. The student immediately concludes that something went wrong in the experiment because the graph or table shows behavior that is elastic for low speed but appears to violate a principle for high speed collisions. Okay. Give an example of a graph or table that indicates nearly elastic behavior for low speeds but appears to violate a principle for high speed collisions. All right, well, how could it violate physics, right? That's kind of like what you're looking at. Oops. So let's think about that. So if you had a perfect ball, then the bounce height would always equal the drop height. Okay? And that's if you have a perfect ball. Now, the violation should be easy to kind of notice here. A violation would be if the bounce height is greater than the drop height, because that would show that the final kinetic energy is greater than the initial kinetic energy. So this is the kinetic energy from the floor, and this is like as it's coming off of the floor. This one is when it's falling down to the floor, the one on the right. And so they want us to kind of sketch a graph here. I'll do this shortly or quickly. Alright, so we'll do the same thing ahead. So I had the bounce. I'll do this very shorthand. This would be drop. Okay, so basically, oh my gosh. What's going on? Okay. So this would be kind of for low speeds, right? When it's low speeds, it said it was elastic. So that means that our slope would equal to 1. So let's kind of show that. But for higher speeds, it says it breaks law of physics. Well, that would show that the bounce height is greater. So, as long as we just kind of show this relationship. Okay, sorry about this, guys. So basically, oh, not orange, did not mean to. Basically, what you want to prove is that, well, here the slope is greater than 1, which is impossible. Okay. Well, this is kind of the part 2. Just says state 1 physics principle that appears violated, or several physics principles that might appear to be violated. But you only need to identify one. Okay. Well, I already said this because it's impossible for the final kinetic energy to be greater than the initial kinetic energy, because that would show that there was more. The reason why that's impossible is then that would then include that, the final height is greater than the initial height. That also means that that somehow you gained energy, which you cannot just acquire energy, in an experiment. So this is impossible because energy cannot be created or destroyed. And this is just by the law of conservation of energy. Okay. Well, that's all I got for you. This is how you get a perfect score.